Hello everyone, this is Sridhar Chintala, Assistant Professor of Physics, ABV Government Degree College, Janagam. So far I'm making a video lectures on modern physics for the sixth semester of BSc Physics. And this is the video made for the second semester students, that is from the thermal physics, and the topic is the statistical mechanics. So in this video lecture, we are going to discuss about the statistical mechanics, the basics and postulates of statistical mechanics, and the definition of a space, gamma space and mu space, and as well as the ensemble. So this is from BSc Physics, Thermal Physics, second semester, and Unit 4, the statistical mechanics. So as far as the statistical mechanics is concerned, the statistical is nothing but the numbers. So how the numbers are distributed, what is the probability of a distribution, that is given by the statistical mechanics. And the statistical mechanics is the branch of science which provides a framework for relating the microscopic properties of individual atoms and the molecules to the macroscopic or bulk properties of materials that can be observed in everyday life. For example, if we consider a gas, we measure pressure, we measure volume, we measure temperature. So those are called the macroscopic properties or bulk properties. So how they are related to the microscopic properties of individual atoms, and that is provided by the statistical mechanics. So therefore explaining thermodynamics as a natural result of statistics and mechanics is at the microscopic level. So in particular, it can be used to calculate the thermodynamic properties of bulk materials from the microscopic data of individual molecules. So statistical mechanics is the application of probability theory, which includes mathematical tools for dealing with large populations, to the field of mechanics, which is concerned with the motion of particles or objects when subjected to a force. So this is the one branch of science which applies to a large populations, and we include mathematical tools to tools for dealing the large populations, and we try to calculate the probability of the distribution. So this is about the statistical mechanics. And in order to discuss about the statistical mechanics, we have to have knowledge of some definitions. And the first one is the macro state. So it is that of the system which can be perceived by experiments. So we can see in physical. So it is an isolated state of system, not influenced by external agencies, and can be defined by certain values of pressure, temperature, and volume. So these are the macroscopic properties. With this, we can define a system, and that state is called the macro state. So macro state can also be defined in terms of its microstructure, example by the specification of number of molecules. So macro state does not distinguish individuality of particles. So macroscopic property or macro state gives the property as a whole of the system. And then microstate. Each macrostate can have several microstates associated with it. Microstate is that state of the system where the individuality of the particles is not ignored. So in a macrostate, there are several number of microstates. Each microstate is characterized by some properties. So the individuality of the particles is not ignored in microstate. So hence the microstates are affected by change in position, momentum, and energy. that is the mutual interaction of individual particles. So these states, however, cannot be identified by any physical experiment. So we cannot observe the microstates of a macrostate, since the experiments cannot observe these microstates. So in actual physical problems, we deal with extremely large number of particles, that is of the order of 10 to the power of minus 25 meter cube, whence the number of microstates can be unimaginable. And then the accessible microstates. Among all the microstates, what are the accessible microstates that is given by the accessible microstates? So those microstates which follow stipulated conditions like number of particles is conserved, energy is conserved, system has finite extension, are called the accessible microstates. For every microstate, we should have these certain conditions. One is the particle is concerned, number of particles is conserved, and energy is conserved, and the system has a finite extension. So these are called the accessible microstates. And then the state of equilibrium. What do you mean by equilibrium? So it is the steady state of an isolated system where the values of P, V, and T do not change with the passage of time. In such systems, no energy is given or taken. In statistical terms, equilibrium state corresponds to that macrostate which has maximum microstates. So the state of equilibrium is defined as the state of the system where the values of pressure, volume, and the temperature do not change with the passage of time. So the equilibrium state corresponds to the macro state which has maximum microstates. And then events. So when an operation is performed or is allowed to take place, the occurrence of certain complexion or configuration or arrangement of the system at one such trial is called an event. So when number of trials is increased, the probability of certain event may increase. So what is an event is the probability of occurrence. So when an operation is performed or allowed to take place, the occurrence of certain complexion or the configuration or the arrangement of the system at one such trial is called an event. For example, if you take a die, so if you throw a die, so it has 6 faces. So any number may come. So from 1 to 6, we may have 1, 2, 3, 4, 5, 6. So any number. So the occurrence of any number is called as an event. So if we increase the number of trials, we get the probability of getting one number is more. So these are the basic definitions to discuss about the statistical mechanics. And then the postulates of statistical mechanics. In order to study or in order to understand the statistical mechanics, we have to have some assumptions called as the postulates of statistical mechanics. So the fundamental postulates of statistical mechanics are: one is all gases are composed of molecules which are in a state of constant random motion. All gases are composed of molecules which are in a state of constant random motion. So all the molecules in a gas are not at rest, rather they are moving here and there. So that is the first postulate. And the second one is the total number of molecules in a gas is constant. So when you consider a gas, if it is consisting of some n number of molecules, that n number of molecules will be constant. And the total energy of the system is also constant. Then all the elementary cells are of the same size. So whatever the gas or whatever the system you consider, and the unit structure for that gas is same for all the structures. So all the accessible microstates corresponding to possible macrostates are equally probable. So already we have the definitions of microstate and macrostate. So in each macrostate, there are several number of microstates which are characterized by individual properties. And if when you consider a microstate, all the microstates corresponding to the macrostate are equally probable. So the equilibrium state of a system corresponds to the state of maximum probability. We already discussed this. The equilibrium state is this, or this equilibrium state of a system corresponds to a macro state with the number of maximum microstates, allowed microstates. So that is the equilibrium state corresponds to the maximum probability. So these are the postulates of statistical mechanics. And then we are moving to the definition, the important one in the statistical mechanics, the phase space. The instantaneous position of a single particle is determined by the three independent coordinates x, y, z, and the instantaneous motion is described by the velocity components vx, vy, vz, or more conveniently by momentum components px, py, pz. So therefore, the state of a single particle is then completely specified by above 6 coordinates. We may imagine a 6-dimensional space, and the position of a particle in this space will be described by a set of 6 coordinates x, y, z, and px, py, and pz. So this 6-dimensional space for a single particle is termed as phase space or mu space, where mu stands for molecule. So this is the phase space, which is used to describe a system of n molecules. And in order to describe a single particle, we should have the momentum coordinates as well as the position coordinates. As far as the position coordinates are concerned, there are 3 coordinates, and momentum coordinates, there are 3 coordinates. So in order to specify a single molecule or a single particle, we should have 6 coordinates. So in that way, this is called a 6-dimensional space, and it is termed as the phase space or the mu space. Since we are specifying each and every molecule, so that is called the mu space. That mu stands for molecule, and this is the mu space. In each and every single particle is determined or defined by a point in the phase space. So the instantaneous state of the particle in the phase space is represented by a point known as phase point or a representative point that we saw already. The number of phase points per unit volume is called phase density. For a system of n molecules, the instantaneous state is represented by a set of n points in the mu space, one for each molecule. The total number of translation degrees of freedom is then 3 into n is equals to 3n. So one can construct a phase space for all the molecules which has n dimensions. So if we consider one molecule, it will have 3 dimensions, and if you consider n molecules, we'll have 3n dimensions or 3n degrees of freedom. So if we construct a phase space for all the molecules, that phase space will have n dimensions, and the n dimensional space is named as the gamma space. So it is represented by 3n coordinate axis and 3n momentum axis. The 6n coordinates represent the position and momentum of all the molecules at a given time. So the number of states available to a particle depends on the available volume in the phase space. For a continuous phase space, any finite volume contains an infinite number of states. So, but the uncertainty principle, it is delta x into delta p approximately equal to h by 2 pi, state that we cannot simultaneously know both position and momentum. So we cannot say that particle is at a mathematical point in phase space. So the number of states available to a particle depends on the available volume in the phase space. For a continuous phase space, any finite volume contains an infinite number of states. But these infinite number of states, all the number of states are not possible. So from the uncertainty principle, that we cannot simultaneously know both position and momentum, so we cannot say that particle is at a mathematical point in phase space. So an element of volume, if we consider dV, so that is characterized by dx, dy, dz, dpx, dpv, dpz. So this is the volume which contains an elemental volume. It is defined in the phase space. The smallest element of volume is called a cell, and it is constrained by the uncertainty principle to be h cube for a particle having 3 degrees of freedom and hf, h to the power of f, for f degrees of freedom. So if you consider a cell in the statistical mechanics, the volume of that cell is constrained due to the uncertainty principle, and the volume of each cell is limited to h cube for a particle having 3 degrees of freedom. And if we consider the f degrees of freedom, a particle with f degrees of freedom, the volume of that unit cell is constrained to h to the power of f. So if we think of the phase space as divided into cells, each of size h to the power of f, then the set of microscopic states contained in a volume element delta gamma is equals to delta gamma by h to the power of f quantum states. So if the whole volume of the microscopic states is delta gamma and each cell is having a size of h to the power of f, and this whole volume is divided into number of quantum states, and each quantum state is equals to delta gamma by h to the power of f. So in this sense, a discrete quantum state occupies a volume equals to h to the power of f in the cellular quantum mechanical phase space. So this is called the phase space, and this is a cell in which a phase point is represented. So the volume of each cell is constrained by the uncertainty principle, that is delta x into delta p is almost equals to h cut. So from that we can have the volume of each cell as the h to the power of 3 from the uncertainty principle constraint. So if the whole volume of the microscopic state is delta gamma, then the volume of each cell is given by delta gamma by h to the power of f. And then classically, at a given instant of time, the microscopic state of the system containing n particles is given by single representative point in a 6n dimensional phase space. And all the phase points with same macroscopic properties lie on a surface called energy surface in this phase space. So as a result, the representative point traces a phase line on this surface in the phase space. So each point on the phase line represents one such possible microscopic state. For the measurement of macroscopic variables like P, V, T, etc. of the system, one has to find the time averages over all the phase points spanned by the system during this time interval. And Gibbs replaced this time-independent character by another concept that was taken to be existing all the time, the ensemble. and then taking the ensemble average instead of time average. So this is the phase line. So this is from t is equals to 0 and it is traversing a line as the time is changing. So on this phase line, each point on this phase line represents a microscopic state. So if we represent a microscopic state with a dot, so all the phase lines, all the phase points with the same macroscopic properties lie on a surface called energy surface in this phase space. As a result, a representative point traces a phase line on the surface in the phase space. So this is called the phase line, and each point on the phase line represents a microscopic state. And then the concept of ensemble. What do you mean by ensemble? Is it is a collection of a number of microscopic systems which are interacting with each other or may not interact with each other. So as mentioned above, each phase point on the line corresponds to different times as their variation in time in succession constitutes the phase line. Gibbs replaced this time-independent picture by a static picture in which the entire phase line exists at one time. So this is the phase line in static picture. So each phase point represents a separate system with same macroscopic properties like number of molecules n, volume v, energy E, and as a system of interest but at different microscopic states. So each phase point represents a separate system with the same macroscopic properties but at different microscopic states. So a large number of such similar non-interacting independent systems when imagined to be grouped together is called an ensemble. A large number of such similar non-interacting independent systems when imagined to be grouped together is called an ensemble. So all the members of an ensemble are identical in features like number of molecules, volume and energy, etc., and are called the elements. So the members of ensemble are called as the elements. And all the elements related to the same macroscopic state but different micro states. So they differ from one another in position and momenta coordinates of individual molecules. So this is an example of the ensemble. So each cell is characterized by NVE, that is the system of interest, and collection of such system of interests, a number of such system of interests is called an ensemble. So the members of the ensemble are called as the elements of the ensemble, and each element is characterized by same macroscopic properties but with different microstates, and microstates are characterized by their position and momenta coordinates of individual molecules. So through the concept of these elements, we can use the mathematical tool, the theory of probability, in order to arrive the parameters that characterize the whole system under observation. So an ensemble average is the average at a fixed time over all the elements in an ensemble. This average closely agrees with the time average provided the system has got large number of molecules and the elements that form the ensemble is also large. And some of the known ensembles we discuss here. The first one is, since an ensemble is an assembly of macroscopically identical but mutually independent systems, a change in macro parameter like volume, pressure, energy, number of molecules may lead to another set of systems. So the first example of known ensembles is uniform ensemble. So those ensembles which have same density in phase space are called uniform ensembles. Hence, if delta n represents the number of systems in the volume element delta gamma, we have for a uniform ensemble as limit delta gamma tends to 0, 1 by delta gamma into delta n by n is equals to constant. So uniform ensemble is such an ensemble in which all the uh, molecules or all the members of the ensemble are having same density in phase space. So that is the uniform ensemble. And then the microcanonical ensemble. So in these ensembles, the energy of their member system remains constant. So energy remains constant means they do not interact with each other or with the surroundings. So when you consider the members of microcanonical ensemble, each member is isolated from one another, and in turn all the members are isolated from the surroundings. So that is the energy of the system member system remain constant. So they are free from external effects. The ensemble is thus conceptually an idealized one and can be represented by a function that depends only on the energy. So every member is separated from the other by a rigid, impermeable and insulated walls. The density of phase points within each member system is uniform and is 0 at the walls. So physically, we may view the microcanonical ensemble as a perfect insulating enclosure encompassing several isolated systems. It is suitable for ideal gases. So this is the ensemble, microcanonical ensemble. So all the separating walls are rigid and impermeable walls and insulated from each other to pass the heat energy. So they are insulated from the surroundings as well as they are insulated between themselves. So this is an example of microcanonical ensemble. So microcanonical ensemble in which the energy of their member system remains constant. That means they do not interact with each other or they do not interact with the surroundings. So this is about the microcanonical ensemble. Next, the canonical ensemble. So in this ensemble, all its members are identical and remain in thermal equilibrium with the source. That is, the members of the ensemble can exchange thermal energy with the reservoir. So thus all the members of canonical ensemble have the same number of particles, volume, and are at the same temperature. So this is the canonical ensemble. So volume, temperature, and the number of molecules are same for each member of the ensemble. So members are shown separated by impermeable but conducting rigid walls, and they are in thermal contact with the source. So the ensemble can be viewed physically as a freezer containing water-filled metal ice cube tray. So this is the canonical ensemble in which the energy, that is the thermal energy, all the members of the canonical ensemble are in thermal equilibrium. And then the grand canonical ensemble, the members of this ensemble can interact thermally, mechanically, and also diffusively with each other and with the heat reservoir. Hence, they are at the same temperature of same volume and at same chemical potential. So V, T, mu, temperature, volume, and chemical potential all are same for all the members of the canonical ensemble, the grand canonical ensemble. And this figure gives the picture of the grand canonical ensemble, and each member is here separated by flexible, permeable, and conducting walls which help to exchange mass and energy between its members, and with surroundings. So the constrained molecules in the member system are of different kinds. So a grain of sugar in boiling water can best be viewed as a grand canonical ensemble. So when we put a grain of sugar, it expands throughout the volume of the water. So that is an example of grand canonical ensemble. And here is the comparison between all the ensembles. So this is the physical property of the system, and this is the microcanonical, canonical, and grand canonical ensembles. So if you consider the volume of member systems same in all ensembles, temperature of member systems same in all ensembles, energy of member systems, in microcanonical ensemble the energy is same, but in canonical and grand canonical the energy is different. And number of molecules in the case of microcanonical ensemble is conserved, canonical ensemble is conserved, but in the grand canonical ensemble it is not conserved. And type of molecules, if we consider, microcanonical ensemble is same, canonical ensembles same, and grand canonical ensemble different, hence produce chemical potential. And use of microcanonical ensemble useful in description of isolated system, and useful in studying systems in contact with the source at constant temperature, and useful in studying non-uniform systems at constant temperature. And feasibility, practically it is difficult, the microcanonical ensemble, practically possible canonical ensemble, and grand canonical ensemble also practically possible. And then the characteristics of an ensemble. So an ensemble is a group of large number of systems. Every member of ensemble is an exact miniature copy of the system under rest. So if you want to describe a system, if you describe one member of the system, it is enough to describe the whole system. So that means each member of the ensemble is an exact miniature copy of the system under the test. And then every member of an ensemble is subjected to the same experimental condition. So there may be three kinds of interaction between the members of the ensemble. One is thermal, related to temperature. Second one is mechanical, related to volume. And the third one is the diffusive, related to number of molecules or chemical potential. So these are three different kinds of interactions between the members of the ensemble. Every member of the ensemble may have a large number of microstates, also called as the dynamic states, due to random motion of its particles or molecules. Ensembles are classified according to the mode of interaction and change in the microparameter of their member system. So we have the ensembles as microcanonical ensemble, canonical ensemble, and grand canonical ensemble, and these are classified as according to the mode of interaction or change in the microparameter of their member system. And then the statistics, as far as the statistics is concerned, we have two classes of statistics. One is the classical statistics and the second one is the quantum statistics. The classical statistics is based on the Maxwell-Boltzmann statistics. So the study of statistical mechanics can be divided into two main classes. One is the classical statistics, that is the Maxwell-Boltzmann statistics, and the second one is the quantum statistics. So classical statistics utilizes the classical results of Maxwell-Boltzmann velocity distribution of particles of an assembly in equilibrium. So classical statistics interpreted successfully the many observed phenomena such as temperature, pressure, energy, etc. But they failed to account adequately for several other experimentally observed phenomena such as blackbody radiation, photoelectric effect, specific heat at low temperatures, etc. So this difficulty is led to the failures of classical statistics forced the issue to in favor of a new quantum idea of discrete energy levels, discrete exchange of energy between systems, and along with a new quantum statistics was envisaged. The quantum statistics was first formulated in 1924 by in the deduction of the Planck's radiation law by purely statistical reasoning on the basis of certain fundamental assumptions radically different from those of classical statistics. So in the same year, Einstein also used the same principles in evolving the kinetic theory of gases as a substitute for the classical Boltzmann statistics. There is a new quantum statistics known as Bose-Einstein statistics came to be accepted. So in 1926, Fermi and Dirac modified Bose-Einstein statistics using additional principle suggested by Pauli in connection with electronic structure of the atom known as Pauli's exclusion principle, according to which no two electrons having the same set of quantum number may be in the same state. In statistical mechanics, this exclusion principle takes the form that two or more phase points cannot possibly occupy the same phase cell. So this led to the recognition of for a second kind of quantum statistics called the Fermi-Dirac statistics. Thus, quantum statistics can again be put into two subclasses. So we have classical statistics, which is using the Maxwell-Boltzmann velocity distribution, and the second one as the quantum statistics. And in quantum statistics, we are having two different kinds of statistics. One as the Bose-Einstein statistics and the second one is the Fermi-Dirac statistics. So the Fermi-Dirac statistics came into the picture by the Pauli's exclusion principle. As a consequence of Pauli's exclusion principle, so we have Bose-Einstein statistics. So this is applicable to identical but indistinguishable particles of zero or integral spins. These are called the bosons. The particles are called bosons, and examples of bosons are photons, pi mesons, and helium atom, etc. are the particles of this kind. So Bose-Einstein statistics is applicable to identical but indistinguishable particles with zero or integral spins. And the next one is the Fermi-Dirac statistics. It is applicable to identical but indistinguishable particles of half integral spins. These particles obey Pauli's exclusion principle and are called fermions. Electrons, protons, neutrons, neutrinos, and helium-3 isotope atom are the particles of this kind. So difference between the classical and quantum statistics, if you consider, the main points of difference between the two types of statistics are: classical statistics apply to a system of identical particles which obey the laws of classical mechanics, whereas quantum statistics applies to a system of identical particles which obeys the laws of quantum mechanics. Classical mechanics, in the classical statistics, volume of the elementary cell in the phase space can be made as small as we please, whereas in quantum statistics, its value cannot be less than h to the power of 3, where h is a Planck's constant of action is given by 6.63 into 10 to the power of minus 34 joule per second. So in the classical statistics, the volume of elementary cell can be made as small as possible. But whereas in the quantum mechanics, the cell size is restricted by the uncertainty principle and it should not be less than h to the power of 3 in the case of quantum statistics. So in other words, the number of cells in the phase space can be made large as we like in classical statistics, but this is not so in quantum statistics. So if you make the size of the cell as small, then we can make the number of cells large in the case of classical mechanics, but it is not the case in quantum statistics. And as the number of cells available in phase space in classical statistics is very large as compared to the number of particles, the occupation index is very much less than 1. So the number of cells in the classical statistics is very large when compared to the number of particles. So the occupation index is less than 1. So there may be empty cells since the number of particles are less than the number of cells. So whereas in the quantum statistics, the number of cells available approximately equal to the number of particles. So the occupation index is equal to 1. So in classical statistics, the particles of the system are considered as distinguishable, whereas in quantum statistics, these are considerable as indistinguishable. So this is about the basics of the statistical mechanics. So far we discussed about the definition of statistical mechanics and some basic useful definitions, what are called macro states and what is called a micro state, and what are allowed micro states, and what is the state of equilibrium and what is called an event, and then the postulates of statistical mechanics, then phase space, and then ensemble, and the definition of ensemble, and the classification of ensembles into microcanonical ensemble, canonical ensemble, and the grand canonical ensemble, and then the different types of statistics, classical statistics and quantum statistics, and comparison of all the three ensembles, canonical, microcanonical, and grand canonical ensemble. So this is all about the basics of the statistical mechanics. Thank you for your patience and thank you for your listening.